Now, turn now to how can we create a probability distribution over the two variables, distance and direction, that will appropriately capture these kinds of characteristics of shot dispersion patterns. According to the definition of conditional probability, we need a marginal distribution, let's say over direction, and then a conditional distribution over distance given direction, and that will characterize the whole shot dispersion pattern. Let's start with the marginal distribution over direction. For this is just simply, I'm going to use simply a Metalog distribution, and I'm going to just do a very quick review of what the Metalog distribution is for those of you that may not be familiar. Metalog is short for metalogistic. Here is the equation X as a function of probability Y of the logistic distribution. The Metalog is simply a series expansion that gives you lots of shape flexibility of these mu and S parameters of the logistic distribution. And like a Taylor series, a Metalog distribution can have any number of terms. You can see here everything from 2-term Metalogs to 10-term Metalogs. Note that in this equation, there are a set of A coefficients. I'll say how to get these A coefficients in a moment from your data. But note that this entire equation is linear, whether you have 2 terms or 10 terms in these A coefficients, and that's an important property. Basically, every time you add an additional term, you add capability for more shape flexibility. By the time you get to 8 or 10 terms, you've probably got more shape flexibility than you'd ever need. This equation, just for those of you with a technical background, is easily differentiable. And what that means is, once you have this quantile function, the inverse CDF shown here, it's easy to differentiate and see the corresponding bell-shaped curve, which could be skewed or have any shape really at all. But those two things are available in closed form. Now, let's talk about where do we get the A coefficients from. And I'm going to start with the golf example. Let's say that for a good golfer, and I think this is true for many good golfers, something in this range, that about if you're doing the best you can to hit a golf shot from 160 yards, maybe about 80% of your shots would end up within this range of 10 yards right of the target and 10 yards left. Maybe one shot in 10 would go farther left than 10 yards. One shot in 10 would go farther right than 10 yards. And I think for most good players, by the time they get to that level, you could say right and left are equally likely. That's not true for most amateurs, but let's say the center of this tree, the median, equally likely to be either left or right. Well, that simple assessment gives rise to, given the linearity of all this, what you see on the right, 3 equations and 3 unknowns. Basically, this simple assessment here are these 3 points on the curve. You've got 3 equations, 3 unknowns. You simply solve those with a little bit of matrix algebra, and you get this simple equation here that is the exact formula for this curve you're seeing shown right here. And there's the bell-shaped curve. This one turns out to be a logistic distribution exactly, which is the Metalog for only 2 terms. But as far as I can tell, that's actually pretty reasonable for most good golfers, or for many good golfers. And if it turns out you're more expert, then you could shrink this range. This also could be skewed. It doesn't really matter. I'm just going to use this simple symmetrical example to get started with. Also, with Metalogs and actually quantile-parameterized distributions more generally, according to the 2011 paper, if you have more data, if you have lots of data, then you can just always fit a Metalog or a QPD to it with ordinary least squares. So that, again, that's a simple closed form calculation. So here are the key features of these quantile parameterized distributions, which I say are a recent innovation that's made this analysis possible. First, they're parameterized by quantiles, which are easy to interpret, and that's extremely important. Secondly, QPDs over the last 10 years and mostly over the last 5 years have been emerging as distributions of choice for practical application. I know of at least a dozen businesses ranging from consulting firms to Fortune 500 companies that use QPDs primarily instead of classical distributions, except in special case circumstances where you needed those distributions. By now, there are more than 100 literature citations to QPD since 2010, and interestingly, most of those are applications. You can see down at the bottom that the earlier papers tend to have more literature citations than the later ones, and that's, of course, not at all surprising. Metalog distributions, which are a subset of QPDs, have some additional properties. One is virtually unlimited shape flexibility. We now have a theorem that says any continuous quantile function can be approximated arbitrarily closely by a metalog. I've mentioned these next two. With metalogs, there's a complete choice of boundedness. They can be unbounded, semi-bounded, or bounded. We're going to use the unbounded today because that's what makes the most sense for this example. There are some limitations that we actually don't come close to running into today, but if you'd like to read about them, you are welcome to do so.